Hello, welcome to Chapter 10, Section 8, called Dilations. This is for Integrated Math 2, or IM2. So a couple things to go over here on the main screen before we get started. The first thing you should see on your screen is a due date. I don't see that on my teacher preview, but you will see it on your student side. The second thing is the number of attempts. We always have unlimited attempts on homework, tests, and quizzes. Number of questions just tells you how many are in this particular assignment. Grading policy is best score, so whichever attempt is the best one is the one you keep. Partial credit is also enabled, so if you answer 1 to 5 questions correctly, you get credit for the one question, or within a question, if there's more than one answer, you can also get partial credit within a question as well. So it's just enabled there. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. That means once I click start, down here in the bottom right corner, I will see a submit assignment button. That is how we finish our assignments, is by clicking that button. And what it means by you can't work on anything else is that the system is actually going to lock out all of your other assignments and your resources until you click that button, because it's trying to leave this attempt open. So it's trying to help you by doing that, because some other schools don't always give you unlimited attempts. We do, so don't worry about that. Click that button as many times as you would like, that submit assignment button. It's going to save your place as well, so you don't have to worry about having to redo anything. As long as you've done a problem and you've clicked check, if you have a little green check mark, it's going to know that. It's going to save your place and start you back up where you left off. So that's a huge reason to click submit assignment. Don't get locked out of all of your other assignments and resources. The second big reason is that it affects the gradebook. So you can see your progress in the class and your teacher can see your progress. Until you click that button, your account is literally frozen. All right, so on the side here, we have explanation, example, and message center. Explanation tells you you're going to lose your question attempt because it's going to literally give you the answer to this question. So I'm going to give you the answer and then let you come type it in. Example, it's going to give you a very close example of what we're looking at. So we get a graph with a line on it, and it's telling us to use a scale factor of 2. It's showing us how to do that, what to do using the tools here, and how to type in the answers. Once we're happy that, we can close it. We can open another one if we'd like to see another one, or we can message our teacher directly from the screen. It attaches a picture so we know where to come help you. All right, let's go ahead and get started on this guy. So this is kind of going back to basic transformations when we kind of did this in previous sections and math classes. So this is just a review of dilations at the beginning here. So the figure below, do a dilation centered at the origin. So remember, origin is the 0, 0 point with a scale factor of 1/4. Then give the endpoints for both the original figure and the final figure. So here's the original figure. And what they want us to do for this is literally just slide it. We have no grabbing tools. We can't shorten it or graph align ourselves. What they want us to do is take the sliding tool and bring it down to the scale factor. So if it's 1/4, I go down to 1/4. So it's 1, 2, 3, 4. If you notice there's 4 sections in here, this is 1/4. If it said for like that example, bring it up to 2, I'd actually go up to 2, and you see it's off the graph, so it doesn't work. It gets too big there, but you bring it down to whatever scale factor, or up to whatever scale factor it's asking you to do. If it's a fraction, it's going to be smaller. If it's a whole number, it's going to be larger. And hopefully we can definitely follow that idea of why. As far as, fractions are parts of a number, so that's small, and whole numbers, that's, more than what you have. So it should be bigger. All right, so if I'm looking at the original figure, the end point on the left, that was 0 and 12. And then the right, that's going to be 8 and 12. And then on the final figure, I have 0 and 3. And on the right, I have 2 and 3. Now, I think we are going to go over this, kind of writing a rule for it. I believe we usually do that quite a bit, where we go through and we look at, how do we actually do this type of thing. So I think it's, probably toward the end, number 4 or 5. But we'll take a look at this right here, because we can kind of see the relationship here. If I'm looking at here, 0 doesn't really have a relationship because we can't see that. But 12 to 3, how does that relate using a 4? Well, if I divide 12 by 4, I get 3. 1/4 of 12 is 3. That's another way of saying that. Same thing with 8. 8 divided by 4 is 2. 12 divided by 4 again is 3. So that's kind of the rule here when we're doing dilations. If we're using a fraction, we're kind of dividing that down. If we're using a whole number, we're going to multiply everything by that number. But you also multiply by the fraction, but fractions mean division. So that's why it's easier to just say 12 divided by 4. All right. So let's keep moving here. So number 2, we're going to look at a figure. So same idea. So for the figure below, do a dilation centered at the origin again with a scale factor of 4. So this is a whole number. I'm going to make this object bigger. So here's my original, and I'm going to go all the way up to 4. I'm just going to slide that over. It's going to dilate it for me. So the shortest side length of the original figure, so if I'm looking here, this one's 2, 2. This one's a little bit more than 2 because it's diagonal, and this one's 1. So it looks like 1 is the shortest. Shortest side length of the final figure, it should be the exact same side length, just over here. So now it's 1, 2, 3, 4. Well, that makes sense from what we were just talking about, doesn't it? Because we were talking about how you can just multiply the pieces. Well, I can multiply the side lengths as well. If this side length is 1 and I'm doing a scale factor of 4, then this side length should be 1 times 4, which is 4. If this one's 2, 2 times 4 is 8. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Same thing would be true here. This one's also 8. And I don't even need to count that because I can see it on the side here. So this one went from 2. 2 times 4 is 8. So whatever this diagonal length is, if I multiply by 2, I would get this diagonal length. That one's a little bit harder because we'd have to use the distance formula on that one. It's not harder, it's just a little bit more involved in counting. So fill in the blank to make a true statement. So the shortest side of the final figure equals blank times the shortest side of the original figure. So exactly what we were just talking about. Everything gets multiplied by 4. So true or false, the original figure and the final figure are not similar. Well, then that means that we didn't do the dilation very well. Because dilating just means that we're making it larger or smaller. We're not changing the shape. So they should definitely be similar. So that not throws us off a little bit there. All right. Is it not going to load again? Oh, there we go. Okay. I was worried it was freezing again, like it did on the last video. All right. So in each part, dilate the solid figure exactly onto the dashed figure. If it's not possible, click not possible. So in order to dilate a figure from one to the other, they need to be the same shape, just like I said on the last one. A dilation doesn't change the shape, it just changes the size. So if we look at these two shapes, they are not the same. This is definitely a rectangle, this is definitely a square. So I'm already going to click not possible. There's no way I could dilate one onto the other. And the same problem here, actually, it's kind of funny they gave us two of the exact same problem. This is definitely a rectangle and this is definitely a square. So again, it's not possible. So I'm going to go ahead and click check, and I'm going to try another one to see if we can actually get one that we get to dilate on. Okay, so these two could definitely work. Although they are the same shape, if I try to move this one down, it's going to get smaller and smaller. So I can't really dilate it. That would be a translation. So this one, again, is going to say not possible. It's possible to move one square into the other. They are the same size and shape. But remember, with the dilation, I need one to be small and one to be large, and I'm dilating one to the other. So with this one does look like it may work if I dilate it up. Ooh, that did work. So I just had to keep going until it snapped into place there. So that's what we're looking for, is the same shape, but different sizes, and I get to move one into the other. All right. So now that we've actually gotten to see that, okay, so draw the image of the following triangle after a dilation centered at the origin with a scale factor of 2. So what they're not showing us was we don't have a little slide bar anymore. We have to do this all on our lonesome now. So no more of those cute little slide bars. We have to figure out the calculations here. So I need to know these the distances here, or not distances, the coordinates. So this is 6 and 9. 6 and 9. And this guy is 8 and 6. 8 and 6. And then this guy up here, and I'll draw our little triangle. Not doing a very good job, but close enough. This guy up here is 8 and 9 again. 8 and 9. Okay. So in order to know the points, and I know on the notes page when we did it, we had a shape that looked like this. It wasn't actually connected. Like this was open. So you would just do this point. You still do the 3 points. You just aren't going to connect that when you redraw it. Okay? So just whatever shape it is, look at the vertices. Look at those corners. And you're going to take everything and you're going to multiply it by 2. That's exactly what we kind of been talking about this whole time, right? That's the pattern when we're doing dilations, is we're either multiplying by a whole number or we're dividing by the denominator and the fraction. So if I multiply everything, 2 times 6 is 12, 2 times 9 is 18, 18 times 2 is 16, and this is times, not minus, sorry. It's like minus signs. 18 times 2, or sorry, 9 times 2 is 18. If you have me in class at all, you know I do that all the time on accident. We get 16 again here, and we get 12 here. So those are my coordinates. I'm going to go ahead and graph those. And you can use the coordinate graphing tool if you want, the plot a point. But this one's pretty easy to go. 12 and 18, 16 and 18, and 12 and 16. Uh-oh, went wrong there. 16 and 12. I don't know why I did that backwards. There we go. Ooh, excuse me. So does everybody make mistakes? Of course they do. You just kind of go back, take a look at it, and I didn't realize for some reason I flipped that around in my head and I did 12, 16 instead of 16, 12. Does it happen? Sure, but I could tell right away something was wrong with my triangle and I needed to go back and fix it because I could tell that side wasn't going to be long enough. Because it should definitely be bigger. I'm dilating it, but I should be able to see that they are similar triangles. I've increased the side by a factor of 2, right? So if this is 2, this side length should be 4. If this is 3, this side length should be 6. So we should be able to see that scale factor happening there. All right, one more. Okay. So this is the one where we're going to kind of go through and look at the rule. We've already been talking about the rule a whole bunch here, so I hope this definitely starts to make sense at this point. And it should hopefully be a lot of review. We've gone over dilation quite a few different years in a row. So a dilation centered to the origin with a scale factor of 3 halves is applied to triangle DEF. And that's a little misleading because 3 halves, yes, it's a fraction, but it's an improper fraction. So we're actually making the triangle larger, even though it's a fraction. It's really 1.5 if we turned it into a decimal. So just, pay attention to the numbers they're giving you. So we have our result here, which is DEF prime, just little tick marks with it, right? We have those little apostrophes so that we can see that it's the final figure. So the arrows below show the coordinates on the left are mapped to the coordinates on the right. Fill in the blanks to give the coordinates after the dilation. So for D, we just want to say, okay, well, what is the coordinate here? So it's 9 and 6. So we have 9 and then we have 6. And then we have, for E, we have 9 and we have -4. So 9 and -4. And then we have F became -3 and -6. -3 and -6. So the main thing we want to make sure, and this one's a little harder to see because it's a fraction, so we don't quite see it as easily as we would maybe if it's just a whole number. But we are in fact multiplying, just like we've kind of been talking about already. So if I have 6 times 3 halves, so I can cross cancel because there's technically 1 under here, so I can cross cancel. 6 divided by 2 is 3, so 3 times 3 is 9. And look at that, we have 9 here. 4 times 3 halves, remember there's 1 under, I can cross cancel, and this becomes 2. 4 divided by 2 is 2. 2 times 3 is 6. And look at that, we have a 6 here. So I can do that with each one of these. 6 again, I don't have to do that again, it would still be 9. Negative 2 times 3 halves. Negative 2 divided by 2 is negative 1. Negative 1 times 3 is negative 3. Uh-oh, I think that's where I went wrong there. Yep, that should be negative 3. Okay, I'm glad I checked it real quick because that would have been wrong. And then for this one, we have negative 2 again, so we're going to get negative 3 if we multiply this again. Negative 4, so we'd actually get the same thing as 4, but it would just be negative on this one. So we can see that works out each time if I multiply by 3 halves. So I just need to make sure I find the rule down here that's showing 3 halves. So I wanted to make sure it's 3 halves, not 2/3, or, you know, flip-flopped. It shouldn't be flip-flopped at all. They should both be 3 halves times x and then times y. So this guy definitely works. I have 3 halves here and 3 halves here, but they put the x and the y backwards. We're not doing that. That has to do with another type of transformation. Dilation, the x and the y do not move in that way. All right, so that was section 8. I do believe that is the end of chapter 10, and I will see you in chapter 11.